have you ever seen a system, a machine, just go completely haywire, where it overshoots its target so badly it's almost comical or even a little bit dangerous? Well, today we're diving into a super common but kind of tricky problem in control systems that causes exactly that. It's a hidden issue, and it can lead to some seriously dramatic results.
So here's how we're going to break it all down. We're going to start with a really simple, real-world problem. Then we'll play detective and diagnose the root cause. After that, we'll get into the nitty-gritty of why it happens. And finally, we'll look at the seriously clever ways engineers have figured out how to fix it.
All right, section 1. Let's set the stage with a scenario I think we can all picture. A car's cruise control system that's on a mission that's about to go really, really wrong. Okay, so you're cruising down the highway. You set your cruise control to a nice, steady 120 kilometers per hour. Simple, right? The system's only job is to keep you at that exact speed. But then you come up on this massive, steep hill. Your engine, it's a good engine, but it's giving it everything it's got. The pedal is literally to the metal, but you're only managing 100 kilometers per hour. It's physically maxed out. Now, inside the car's computer, the PID controller, that's the brain of the operation, it only sees one thing. We're 20 kilometers per hour too slow. It has no idea the engine is already at its absolute limit, so it just keeps demanding more, building up this massive imaginary request for power. It's basically screaming, more gas, into a system that can't give any more.
So what do you think happens the second you get over the top of that hill and the road levels out? Well, that huge demand for power the controller built up is finally unleashed. The system keeps the pedal floored for way too long, and suddenly, whoosh, your car lurches forward, blasting way past your target, all the way up to 140 before it can even think about correcting itself. That is a serious overshoot.
So that dramatic overshoot, it's not just some random computer glitch. It has a very specific name, and it is the entire reason we're here today. So let's get into section 2 and properly meet the culprit. And here it is, integral windup. It's what happens when the controller's calculated desire for more power completely disconnects from the system's physical reality. That integral term in the controller just keeps counting up the air, getting wound up tighter and tighter, like a spring, storing all this energy that is absolutely nowhere to go, yet. The best way to think about this is with a simple bucket. Your goal is to fill the bucket. The problem is the faucet is already open all the way. It's saturated. Windup is like you, not realizing it's fully open, just keep cranking on that handle, trying to turn it even further. Then when the bucket is finally full, you can't just instantly shut it off. You've over-tightened it, and so water spills everywhere. That's your overshoot. Okay, so how does this windup thing actually happen? It's not just one single fault. It's more like a perfect storm, a combination of two very specific conditions that have to happen at the exact same time. And this slide, this really gets to the heart of it. It's a total conflict. The controller, sitting in its digital world, calculates this absurd command, like, I need 300% power. But the actuator, that's the physical part, the engine throttle, or maybe a heater element in an oven, is stuck in the real world. And it's saying, look, I'm sorry, I'm already at 100%. That's all I've got. So this conflict happens because of a persistent, ongoing error. You can trigger it by asking for a huge change all at once. Imagine telling your home thermostat to take a room from 20 degrees to 100 degrees Celsius right now. The heater will be on full blast for a long time. Or it could be a big disturbance, like opening an oven door and letting all the heat rush out. And of course, just like in our car example, it can be caused by simple, unavoidable physical limits. All right, enough about the problem. Let's talk solutions. The good news is, this is a super well understood issue, and engineers have come up with some really elegant ways to stop it from ever happening. These are called anti-windup techniques. So all of these methods have the same goal: stop that integral term from running away when the system is maxed out, but they all go about it a little differently. We're going to look at two of the most common ones. You've got integral clamping, which is basically like hitting the freeze button. Then there's back calculation, which is a bit smarter and actively reduces the value. There's another one, conditional integration, but really, clamping and back calculation are the heavy lifters you'll see out in the wild. So, integral clamping is the most straightforward fix you can imagine. The logic is dead simple. If the system detects the output is at 100%, it just tells the integral term, okay, stop counting. It freezes the value right where it is. That's it. That way, when you finally do get over that hill, the controller isn't all wound up and it can respond almost immediately. Back calculation, on the other hand, is, well, it's a bit more elegant.
Instead of just freezing the integral value, it's constantly looking at the difference between the controller's fantasy, that 300% gas command, and the actuator's reality of 100% gas. It takes that 200% difference and uses it as a feedback signal to actively unwind the integral term, bringing it back down toward a realistic number while the engine is still maxed out. This means you get an even faster, smoother recovery. It takes a little more processing power, but for systems where you absolutely have to minimize that overshoot, it's the way to go.
And that's really how you tame the machine. You give the controller a dose of reality. So that leaves us with a final thought. Now that you know the signs to look for, a system hitting its limit and then dramatically overshooting, where else might this hidden problem be lurking? Think about your thermostat at home, industrial robots, chemical processes. It's everywhere. In fact, most modern control systems, like the PLCs and DCS systems that run entire factories, have these anti-windup features built right in. Because in the real world, preventing this kind of overshoot isn't just a nice-to-have, it's absolutely critical.